In this lecture, we are going to see another new concept which is called convergence, convergence of the random variables. Okay, and then we are going to talk about something regarding the limit theorem. So, in this particular chapter, we are going to see four kind of convergences, mode of convergences, basically four kind of mode of convergences, and then we will see some relationship among those convergences and some theorem regarding different property of the convergences, those convergences, and some examples. That is basically the first part of this chapter, and the next part, second part of the chapter, we are going to see two very, very popular theorems. One is known as strong law of large numbers, and another is known as central limit theorem. Okay. So before going into the mode of convergences, just recall that in your basic math course you have seen the convergences of the function of real numbers. So if you have a sequence of real number fn, you know what do you mean by the fn converges to another function f. Now in this case, also again you have different mode of convergences, like we talk about pointwise convergence, we talk about uniform convergence, and those kind of convergences are there. Now in case of the random variable, you know random variable is also a function. So when I am talking about a sequence of random variable, that means that is again a sequence of functions. So when we talk about this, then also different kind of modes come into mode of convergences come here, like we have defined mode in case of a function sequence of functions from R to R. Obviously, when we are talking about sequence of functions from R to R, there is no kind of probability attached there. So now we have different we have probability attached to random variables. So we have probability attached to sequence of random variables also. So that is another part which we can talk about. So first point is that you know uniform convergence, you know pointwise convergence in case of sequence of functions from R to R. Obviously, if your random variable, the sequence of random variable xn is defined on R, definitely those kind of convergences like uniform, like pointwise we can talk about. But here our main aim will be not talking about those kind of convergence, but we will going to talk about some convergence where probability is involved. Okay, we are going to talk about some convergence. Basically, we are talking about four mode of convergence where probability is involved. Because when I am talking about that random variable, there is a probability. So with the sequence of random variables also, there will be a probability. Okay, so let us see these four main convergences, main mode of convergences. So the first one we'll start with is called almost sure convergence. So what is almost sure convergence? First, let me read this definition and then I'll explain it. So first thing is that I have a sequence of random variables, and this sequence is defined on a probability space SFP. So that basically means that x1 is defined on the probability space SFP, x2 is defined on the probability space SFP, x2, x3 is also defined on the same probability space, and so on and so forth. So all the random variables in this sequence defined on the same probability space. X is another random variable which is again defined on the same probability space. Okay, x is also defined on the same probability. So I have a sequence of random variable defined on a probability space. That basically means that all the random variables in the sequence defined on the same probability space, as well as x, another random variable which is also defined on the same probability space. We can talk about this almost sure convergence if this thing holds true. This thing holds true. That means if all the random variables concerned are defined on the same probability space, then we say that the xn converges almost surely or with probability 1 to a random variable x if this quantity holds true, if this equality holds true. What this equality means? Note that inside this probability, the set is nothing but I am taking the collection of all those omegas in S, all those omegas in sample space, such that xn omega converts to x omega. Now notice that when I fix my omega here, xn omega is a sequence of real numbers. So, and similarly, x omega is also a real number. So this convergence basically means that a sequence of real number converts to another real number. Okay, so that basically that this convergence meaning we know that what do we mean by if I have a sequence of real number n, what do we mean by this converges to a real number a, that we know epsilon delta definition, we know all those definitions. Okay, so this convergence is basically nothing but a convergence of real number, and for each omega it is a sequence of real number, it is a real number. So this is a convergence of real number, sequence of real numbers. So I am now collecting all those omegas in the sample space for which this sequence of real number converts to this real number. Then if I make this collection, if I see this, the probability of this collection is 1, we say that the xn converts almost surely to a, or xn converts with probability 1 to a. Okay, so I hope the definition is okay. So definition again, just repeat it, that I need all the constant random variables need to be defined on the same probability space. Then only I can talk about almost sure convergence of xn to x, and we say that xn converges almost surely to x if probability of the set where xn converts to x, that probability of the set is 1, we say that xn converts to x almost surely. Okay, so let us take another one example which may be helpful to understand the definition much better. So we start with our sample space is 0, the interval 0, 1, sigma field is Borel sigma field over 0, 1, and P is basically a uniform probability on the Borel sigma field. So that basically means that we are talking about if you take any subset of 0 and 1, any interval from 0, 1 which is a subset of 0 and 1, then the probability of the interval I is basically nothing but the length of I. Okay, so we have seen this example previously, and we have just pointed out this thing that, well, if I define P of I for all interval in S, then that can be uniquely extended for all sets in the Borel sigma field over the 0, 1. Okay, and in this case, this probability measure for each interval in S is nothing but the length of I. So with this setup we start, and then we take the random variable xn is defined by this one. So what is this? This is nothing but we have basically example 4.1. So example 4.1. So we have basically the x in omega we have taken as the indicator function of the set 0 to 1 by n omega, and it is true for all n equals to 1, 2, 3, 4, and so on, so forth. So that is basically nothing but for the nth one, I have the interval 0 to 1. For the nth one is 1 by n here. So this random variable, the nth random variable 1 is here and 0 here. So xn is equals to 1 here, 1 on the interval 0 to 1 by n, and xn is 0 over the interval 0 to 1. So basically now if I see the sequence, that is basically for the first one I have half here, and the first random variable is 1 here, it is 0 here. Then I have 1 by 4, then I have 1 by 3, the second random variable is 1 here, 0 otherwise. So basically if I start with n equals to 1, so x1 is 1 over the interval 0 and 1. For all points in 0 and 1, the x1 is 1. So x1 is 1 for all omega belongs to the interval 0 and 1. Then x2 is 1 for all omega in the interval 0 to half, and it is 0 otherwise. Okay, and so on it is going. So basically I am having that 1, then half, 1 by 3, 1 by 4. In this way the 1 by n points are going here, and as I increase n, this xn will be 1 in a small interval here, and it is 0 otherwise. Okay, so that the I hope that the in that the random variable, this definition of the sequence of random variable is fine with everyone. So now you see that intuitively it means that basically this random variable is nothing but as I increase it will be zero for most of the values in 0 to 1, and on the very small interval here it will be 1. So that intuitively tells that if this random variable converts, it should convert to 0. So let us now check that whether it is actually converting to 0 or not. Okay, let us now check that if it is actually converting to 0 or not. Okay, so we want to check if xn converges to x almost surely, where x omega is 0 for all omega belongs to x. Okay, so if this random variable is 0, the x random variable is 0, so we try to check that whether xn converges to x almost surely or not. Okay, clear? So this one is very easy to see. This convergence is actually there because fixed omega, first fixed omega belongs to S. Any fixed omega belongs to S. What I can do is that I can find out a n naught. We can find out a n naught. We can find n naught obviously which belongs to n, the set of natural numbers, such that omega is greater than 1 by n for all n greater than equals to n naught. So that basically means that you take any omega in the interval 0 and 1, you take any omega in the interval 0 and 1, I can take n large enough so that 1 by n are less than omega. Okay, so that means that for this omega, so that means that xn for this omega, xn omega is equals to 0 for all n greater than equals to n naught. And what does this mean? This means that xn omega converts to 0. Okay, xn omega converts to 0 as n goes to infinity. Clear? So that basically means that you fix any omega in the interval 0 and 1. You take any omega in the interval 0 and 1. How close to 1 or how close to 0 does not matter. You take any omega in the, not in S, it is basically any omega in the interval in the interval open 0 and close 1, any interval in the open 0 and close 1, because 0, if I take 0, then definitely I cannot find out n such that 0 is greater than 1 by n. So, but without 0, you take any omega in the set of open 0 to 1, you will see that xn omega converts to 0. That basically means that the set collection of omega belongs to S such that xn omega converts to 0. This set is basically the set 0 to 1. Now if I try to find out the probability of this set, this turns out to be 1 because the probability of any interval is the length of the interval, and in this case length is 1. So this is 1, and this shows that the random variable xn converges to 0 almost surely. Okay, the sequence of random variable xn converges to the 0 random variable almost surely. Okay, the proof I hope is fine, and it's not difficult, but the main thing is that what we have done is that we try to find out the collection of all omega in S such that xn omega converts to S. Once I can find out this set, I try to find out the probability of this set, and I try to check whether the probability of this set is 1 or not. If the probability is 1, it converges almost surely. If not, the xn does not converge to x almost surely. Okay. So next mode of convergence is called convergence in probability. So again, in this case also all the concerned random variable need to be defined on the same probability space, and we say that xn converges in probability to a random variable x if for every epsilon greater than 0, probability that mod of xn minus x greater than epsilon goes to 0 as n goes to infinity. So what I am doing here, for every epsilon greater than 0, that basically means that epsilon could be very close to 0, epsilon could be quite big. And the interesting part is obviously epsilon is quite small, because if this quantity is bigger than if this quantity is, if epsilon is big, that actually imply that for small epsilon also this quantity going to be true. But if this is true for small epsilon, that does not mean that this is true for the bigger epsilon. Okay, so I need to check this one for all epsilon greater than 0, and I first need to find out what is the probability that xn minus x, the absolute value of xn minus x is strictly greater than 0, that probability of this event, and then I need to check whether the probability converts to 0 or not. So just put this thing in mind that the main difference between the absolute almost sure convergence and probability convergence is that in this case first we take the limit, first we check that whether the convergence is there or not, and then I take the probability. But in this case first we check that whether the difference is greater than epsilon or not, and then we check whether it converges to 0 or not. Another point I should mention here, notice that probability is a real number, so this quantity is obviously dependent on n, that is a sequence of real numbers. This quantity is a sequence of real number, and in this case I am checking whether this sequence of real number converts to 0 or not. Okay, clear? So let us take examples. Let us take some examples. So the first example is basically, again we start with the same basic setup, that S is 0, 1, F is Borel sigma field over 0, 1, and P is uniform probability over 0, 1. And we will again talk about the same random variable, that random variable is 1 on the interval 0 to 1 by n, xn is 1 on the interval 0 to 1 by n, and is otherwise it is 0. And in this case we can easily see that this random variable converges to 0 in probability also. So in the previous example, example 4.1, we have seen that the random variable xn, this random variable xn converts to 0 is almost surely. Now we are going to see that this same sequence of random variable converts to 0 in probability. Okay, how we can see that? It is easy to see that. Well, notice that if I take x equals to 0, so xn minus 0, which is basically xn mod of xn greater than epsilon. So where mod of xn is greater than epsilon, the mod of xn is only greater than epsilon over the interval 0 to 1 by n, because the xn is 1 on the interval 0 to 1 by n, and 1 by n to infinity it is 0. So the xn mod xn is greater than epsilon for any fixed epsilon greater than 0, the mod of xn greater than epsilon only on the interval 0 to 1 by n. And that completes the proof, because so that means basically probability of this set is nothing but the length of this interval, because here we have taken the uniform probability, and that basically means if I take the limit of this probability as n goes to infinity, that turns out to be 0, and by definition of the convergence in probability, we have that xn converges to x is basically nothing but a 0 random variable, xn converges to x in probability. Okay, let us take another example. This example is basic structure is same, only the random variable is different. Random variable is that now instead of only 1 on the interval 0 and 1, it takes value n on the interval 0 and 1. Okay, 0 and 1 by n. So that basically means that again we have almost same scenario as before, that example 4.3. In the previous example, that the random variable on the interval 1 by n, xn on the interval 1 by n, it was 0, it was 1, now it is n, here it is 0. Okay, so the proof now is again on the same fashion, that well, we are going to again see that where this event going to true will be true for any epsilon greater than 0, xn minus x is 0 taken to be 0, xn minus x is greater than epsilon is only on the interval 1 by n. So like the previous one, in this case also the probability of the event that xn minus x greater than epsilon is 1 by n. That's why the this limit is equals to 0. So xn converges to x in probability. So in these two examples basically shows that, well, even if I multiply this where the random variable is not equals to 0, if I multiply it by n or multiply it by any real number, the convergence still be there, because the probability that xn minus x greater than epsilon, that probability will be smaller and converging to zero as I increase in. Okay. So now, as I already pointed out, that these two things, that convergence in distribution and convergence in convergence almost surely and convergence in probability are different. Sometimes it was in the mind that, well, in this case also I am talking about epsilon greater than zero, so it's kind of a limit I am talking about only. And in the previous example, I almost sure convergence also we can talk about limit, but as I pointed out that in one case I take the limit first and then probability, and the other case first probability and then the limit, and that makes these two convergence quite different. And the next example, example 4.4, actually going to talk about that. So this example is little complicated, but complicated only when I am writing this random variable in the mathematical form. But understanding this random this thing is quite easy if we try to understand with a graph. So what I am doing is that I am defining some sequence of random variables. Notice that I have two suffixes here, but that does not change anything. You can call this is y1, this is y2, this is y3, y4, y5, this is y6, and so on and so forth. So I have again basically a sequence of random variables. So this double suffix only used to write this explicitly in this form. This double suffix is only used to write this thing explicitly in this form, but that is not a problem at all as long as we are talking about the sequence, because you can rename this thing that it is y1, it is y2, it is y3, it is y4, and so on and so forth, and that works with us. Okay. So how we define this random variable? Just understand the definition of the random variable. The rest of the part is quite simple. So, so this way we proceed. That we take the interval 0 and 1. Again same setup, that f is 0, 1. F is Borel sigma field over 0, 1, and P be the uniform probability. P be the uniform probability measure. Okay, the same setup we start with. Now, the definition of the sequence is as follows: that we start with the interval 0 and 1. First, we divide the interval into two equal parts. So, 0 to half and half to 1. The first random variable is 1 on the first interval, 0 otherwise. The second random variable is 1 on the second interval, and it is 0 on the otherwise. Okay. Now, next what we did, we now divide the interval into equal 2 square, which is 4. So 4 equal parts. So 0 to 1 by 4, 1 by 4 to half, half to 3 by 4, 3 by 4 to 1. Okay. Now the third random variable is 1 only on the first interval here. It is 0 otherwise. The fourth random variable is 1 in the second interval here, 0 otherwise. The third one is 1, not third, the fifth one is 1 on this interval, 0 otherwise, and the sixth one is 1 in this interval and 0 otherwise. Okay. Next, I divide the interval into 8 parts, which is 2 cubes, and then again I define the random variable in the similar way, that the seventh random variable is 1 in this interval only, otherwise 0. Eighth random variable is 1 in this interval only, otherwise 0, and so on and so forth. And for the next step, I divide the interval 0 and 1 into 2 to the power 4, which is 16. The 16 equal parts. Then we define the next set of 16 random variables in the similar manner. Okay. So I hope the definition of this thing is fine. And if you try to write this sequence in terms of the mathematics, you can check that this can be written in this form. And the double suffix is only written, only taken to write this thing properly. That's it. Okay. But I hope that this understanding this the definition of this thing is quite you will be able to understand the definition of this. Right? Clear? Now let us try to show that this sequence of random variable converges in probability, and it converges to 0 in probability, and it is not very difficult to see. But before going into the proof of this one, so let us put forward that what I am trying to show here. I am trying to show that this sequence of random variable xmn converges to 0 in probability, but the same sequence xmn does not converge to 0 almost surely. Okay. And if I can show this one, so we try to show that example 4.4, we will show that xmn converts to 0 almost surely, but xmn, I am sorry, this is converts to 0 in probability, this converges to 0 in probability, but this does not converge almost surely to 0. If I can show that, two things it means. That first thing it means that the probability convergence is different from almost sure convergence, and second thing it means that in general probability convergence does not imply almost sure convergence. Okay, that kind of relationship between different mode of convergence we will see, but for the time being, one example we take here that probability convergence does not imply almost sure convergence in general, and that also means that these two convergences are different. Okay, so let us try to prove the first one first, that probability convergence is there, that xmn converges to probability, converges to 0 in probability. Okay, so that part is very easy to see. The reason is that, see, again, what I have to check? I have to check that on which interval xnm is different from 0. Okay, we need to basically, in this case, we need to find out. That we need to basically talk about that x is 0, this is greater than epsilon, so which is basically mean that xmn, mod of xmn is greater than epsilon. Okay, I need to find out where this is true, and you see that this is only true on an interval with length 1 by n. Okay, so this is only true on an interval of the length 1 by n, because you can see it very easily from here that as I go on this for the third step, the each random variable is different from 0 only on an interval of the length 1 by 2q. But the fourth step, it will be only on the interval of length 1 by 2 to the power 4, so 1 by 16, and so on and so forth. So that basically means that in this case, this is only true. This will be true only on a interval of the length 1 by 2 to the power n. So when I try to find out this probability, this is basically same as probability of this, which turns out to be 1 by 2 to the power n. And this quantity goes to 0, and that shows that xmn converts to 0 in probability. Okay, clear? So this sequence converges to 0 in probability. I hope this example is fine with everyone. That it converges to 0 in probability. Okay, that's what we have written here also, that way this thing only true on an interval of the length 1 by 2 to the power n, and as we are talking about the uniform probability, so the probability is 1 by 2 to the power n. Thus this probability converts to 0 in probability. Converts to 0, and that means the sequence xmn converges to x in probability. Okay, now let us talk about almost sure convergence. So for the almost sure convergence, let us point out one thing, that, see, in this case, let me draw this graph here once again. So I have half here, then I divide it into 4 equal parts, then we divide it into 8 equal parts, okay, and so on and so forth. Now you fix any omega here, any omega in 0 to 1. So if you fix any omega in 0 to 1, what happens? For the first random variable x11 omega, for this particular omega, x11 omega is 1, x21 omega is 0, x12 omega is 0, x22 omega is 1, x232 omega is 0, x42 omega is 0, and so on and so forth. So what does this mean? This means that this for any omega in the interval 0 and 1, I have some ones, and for the rest of the random variable it will be 0. So that means if you consider xn omega for any omega, this will be of the form that some zeros then one, again some zeros then one, again some zeros then one. This way it will go on. So that basically means that you take any omega in the interval 0 and 1, this sequence of this real number does not converge, okay. So that's what basically the point here, and that's what we have done here. So you fix any omega in S, then there exists a subsequence of the real number, sequence of this real number that converts to 1, and another subsequence which converts to 0. That means x and omega does not converge for any omega in S. And that shows that if you see the set that omega belongs to S, where x, m, and omega converges, that set is basically phi. So this probability is 0. And if it does not converge, that means there is no question about it converging almost surely. So that random variable do not converge to 0 almost surely. Okay. So the basic idea is that whatever omega you take here, you have some zeros then 1, some zeros then 1, or it may start with 1, but it's some again it come out 0, then again 1 1, then again some zeros, again 1 1, again some zeros, and this way it goes. So x and omega does not convert to any real number, and that shows that this sequence of real number does not convert does not converge, and that means that does not converge to 0 almost surely. Okay, I stop here. In the next lecture, we will see another two mode of convergence: the convergence in arrangement and convergence in distribution. Thank you for listening.